Kia ora koutou. In this video, I'm going to look at 3 different questions with trig integrals. And before I start doing them, we're going to have a look at what method we're going to choose. And these are the 3 questions here. So they're all from 2018. The first one is one where we're told the technique to use. So we're given this integral, we'll make it a bit bigger, and it's the square root of x over 1 minus x. So that looks like it might be a reverse chain rule, but it looks pretty gross. It's not integration by parts. So why do I look at that and immediately say, oh, I don't think it's integration by parts? Well, usually if it's integration by parts, I'm going to have a product. I'm going to have something times something. And one of them will usually be easy to integrate, or at least sort of easy to integrate. And I don't have that here. So this is probably one where I will end up doing a substitution. And they've given me the substitution to use, right? So the substitution they're telling me to use is x equals cos squared theta. If I didn't get given that substitution, I would pick that substitution because I'm working with a square root. And the best way to get rid of a square root is to have a square underneath it. So we're going to do something in here that will get rid of the square root sign. So in this question, first we have to use that substitution and get this, and then we're going to find the exact value of the integral. So here's the next one. The next one is just, this one is a standalone question, and it's just a straight up go ahead and integrate. And in this one, I would use integration by parts, and I'd use it for the reason I mentioned above. So I've got an x times a cos of 3x, and I know that I can differentiate the x, and I can integrate this bit here pretty easily. So that's going to be integration by parts. It might be once or it might be twice. Now, it turns out that it's a pretty straightforward IBP once example. And then the next question is one where first we have to do a little trig proof, and then using that we have to find this integral. So we've just proved that this is equal to this, so we're going to end up integrating this thing here. Now when I look at this, I know this is going to be an easy integral because I've got the pattern of some constant times f dash of x divided by f of x. So it'll be a natural log one, and you're given that as a hint as well. Okay, so now that I've spent 2 minutes talking about the questions, we're going to get on and do them. And once you start doing them, you'll find there are quite a lot of little details that you need to be careful about, especially with this first one here. So we're going to start off with substitution. So what are we going to do? Well, we've got this. So 3/4 here, 1/4 here, square root of x over 1 minus x dx. So we're told to use x equals cos squared theta, and that means that dx by d theta is going to equal 2 cos theta times the derivative of the inside function, which is cos theta. So it's going to be times negative sine theta. So that equals negative 2 cos theta sine theta. I'm looking at that and thinking I could change that into negative sine 2 theta, but I'm not going to do that just yet. So what I need to get here is something to replace dx. So we can do that easily. Dx is equal to negative 2 cos theta sine theta d theta. So that's that first bit done. So that's good. Now we're going to replace x with cos squared theta. So that's that bit done. And now we have to work out what 1 minus x is. And then we have to do our limits. So 1 minus x is equal to 1 minus cos squared theta, and that's sine squared theta. Right, now let's look at the limits and see what we've got here. Well, this is an x limit. So 3/4 is equal to cos squared theta, which gives me root 3 over 2 is equal to cos of theta. Okay, so using our special triangle, what have we got? Well, we've got 1, root 3, and 2, and cos of theta has to be here. So if we want to get root 3 on 2 here, then theta is going to be pi on 6, and we're going to now do the same thing for the bottom limit. So 1/4 is equal to cos squared of theta, 1/2 is equal to cos theta, theta has to equal pi on 3. So my limits are kind of weird because the top one is now smaller than the bottom one, but let's just keep on going. We're ready to put everything back into the integral now. So we've got this 3/4 to 1/4 root x over 1 minus x dx can now be changed over as follows. So it's going to be pi on 6 here and pi on 3 here. We'll deal with that being weird later on. times the square root of cos squared theta over sine squared theta times negative 2, what was it, negative 2 cos theta sine theta d theta. Right, let's clean this up a whole lot. Well, the first thing to remember is that if I want to switch those limits over, I can do that as long as I take the negative of this. In other words, if I've got the integral of beta a from beta a of f of x dx is the same as negative a to b f of x dx. Now, something weird's going on. Yep. Oh no, my OneNote just crashed. Okay, let's just reopen, guys. I'm just going to keep going. I'm sorry, this is really rough. Hopefully it's all about to come back up on my screen. Yep, it is. Okay, so here we go down here. So that integral can be switched like this. So very useful fact from, I think, from AS or from somewhere. Right, so let's do that because it's annoying me that I have the bottom limit being bigger than the top one. It also gets rid of the negative sign really well. So we're going to have the integral from pi on 3 to pi on 6. And we're going to have 2 cos theta sine theta times cos theta over sine theta d theta. That's cleaning up this. That gives me this integral. We're going to have just 2 cos squared theta d theta. And we should recognise that that's going to be best dealt with a double angle formula. So cos of 2 theta is equal to 2 cos squared theta minus 1. That's the one that we want. And we want exactly the 2 cos squared theta. So we're going to replace 2 cos squared theta as follows. We'll have pi on 3 here, pi on 6 here. And now we're going to have cos of 2 theta plus 1 d theta, which is a nice, easy trig integral. It will come from sine of 2 theta times 1/2 plus theta. Right, if you're still not confident with the constants with these trig integrals, it's time that you did a whole lot of Dr. Frost practice, so please send me an email and I will set you some. And now I've got this. I've got 1/2 sine of 2 pi on 3 plus pi on 3 minus 1/2 sine of 2 pi on 6, so that's pi on 3 plus pi on 6. And thinking about my unit circle, sine of pi on 3 is here, so sine theta is y over r, and sine of 2 pi on 3 is here. So these two things are going to be the same. So it's going to be 1/2 times root 3 on 2 plus pi on 3 minus 1/2 times root 3 on 2 minus pi on 6. That gives me a final answer of pi on 3, take away pi on 6, which is just pi on 6. So there we go. So that's quite a long integration problem, but I think a really good one for going over lots of things. So hopefully you're still watching. The next one we're going to do is this pretty straightforward IBP question. Okay, so we're going to find this integral and we have to give our answer in terms of pi. So this one is, I'm just looking at my working, 1, 2, 3, 5 lines long. I'll change pen. So it's from pi on 6 to 0, x times cos of 3x dx. Right, well, I'm going to integrate this and leave this and then integrate this and differentiate this. Right, so it's going to be x times, right, well, what's the integral of cos of 3x? We'll leave a gap to check it. Let's go sine of 3x first. When I differentiate this, I'm going to get a 3 that I don't want, so I undo it with the reciprocal. And I check that I don't have a negative problem. There we go. So that's from pi on 6 to 0 minus the integral of this differentiator, which is 1 times 1/3 sine 3x dx. Oh no, I'm about to lose my OneNote again, I can tell. Okay, come back OneNote. Where are you? There's one particular place on the screen that something weird happens every time. Okay, here we go. So here we've got minus 1/3 sine 3x dx, and we've got those limits. So moving over here to get away from the bad part, we've got x on 3 times sine 3x between pi on 6 and 0. Sorry about the noise. And now I'm going to take that constant out, and I'm just integrating sine of 3x. Right, so sine of 3x integrates to give me cos of 3x, but that's got to be times negative 1/3 between pi on 6 and 0. Sorry, guys. Got everything going on here in the background. Never mind. Right, so we've got x over 3. Just excuse my family for pulling the curtains while I integrate by parts. There we are. There we go. Very good. Okay, peace again. Okay, so we're done. Right, so you can see that this really is a straightforward IBP question, but we've got to substitute in without screwing it up. So let's try and do that. Okay, pi on 6 on 3, pi on 18 times sine of 3 pi on 6, pi on 2. Don't substitute that in your head just yet, or you'll probably screw it up. 1/9 cos of pi on 2 minus, now here we've got 0 because of the x on 3, 0 plus 1/9 of cos of 0, which is of course 1. So look, we've got a bottom limit that does not give us 0. We're left with this. So let's just sketch a silly little graphs of sine and cosine. Sine of pi on 2 is going to be 1. So it's pi on 18 plus 0 for this one, minus 0 minus 1/9. So my final answer, pi on 18 minus 1/9. Now I've only got 4 minutes left, and I've got a whole lot to do on the last question. So let's just see what I'm going to do. I think I'm going to cheat a little bit, and I'm not going to do this proof, even though it is a really nice one. So I'm not going to do the show that 4 marks. I'm just going to do the last little bit of integration, because this video was meant to be about showing you what to do with integration problems. So in here, we've got our limits, and we've got this yucky looking thing to be integrated. But we know from the previous question that that's equal to sine over 1 plus cos x. So this is what I've got to do with that question. Where's my little bit of working for this? Oh, here. Okay. So we've got the integral from what to what? Pi on 2 to pi on 3, sine of x over 1 plus cos of x dx. So I can do this straight away without any substitution. It's going to be equal to, leaving a gap, the natural log of 1 plus cos x. And then here, 1 plus cos x will differentiate to give me negative sine x. I don't want that. I want positive sine x. So I have to put a negative in front of that. So it's going to be that. And then evaluated at those limits, I get negative natural log of 1 plus, right, cos of pi on 2 is 0, minus negative log of 1 plus cos of pi on 3. Cos of pi on 3 is 1/2, so that's 1 plus 1/2, which gives me 0 for this, plus the natural log of 3 over 2, which is simply the log of 3 over 2 without the absolute value signs. So there you go. Now, if you do want to have a look at the proof, though, the proof is one, I'll just do a separate video on it, but there are actually a couple of ways that you can do it where it takes a lot of lines. So it depends on which double angle formula to use, and it's not the one that I would have guessed first of all. So there's your clue for having a look at that question. Well worth a look. It's a really nice proof practice. All right, that's plenty of videoing for today. Please keep on sending in any questions that you've got issues with, and I will keep on YouTubing for you.